Good evening, everyone. So today, today we'll be discussing the doubt and problem solving problems of the questions which is relevant to the assignment question of week 4. So I hope that you all have watched the lectures in the given in the module 4. Just a second. So, uh, this week we'll be discussing the questions which is regarding the problems given in the week 4. So, let's begin with the question. So, as we have discussed till the last class, that will be going like firstly, I'll be asking you the questions, and then you have to solve and you have to guess the answer, or probably you can give the answer with the explanation. And if you cannot, then we will be discussing that what would be the right answer, and then how, and also I will tell you that how to solve the problems. So let's begin with the first question. So the first question is HOPG is different from pyrographite because it offers a lower X-ray transparency, it has highly aligned crystals, it has a lower purity, it is prepared by heat treatment of polymers, while pyrographites are obtained from gaseous hydrocarbons. So, which could be the right answer and why? Can anybody give me the answer? So yeah, what's the answer? So let's discuss this. So here, this slide shows that how can the graphite from pyrolysis of gaseous hydrocarbons. So here the carbon films with higher density and higher La by LC values yield pyrographite. And pyrographite is heat treated to produce industrial grade pyrolytic graphite. Heat treatment can be performed by simple annealing or by hot pressing, and also pyrolytic graphite is called highly oriented HOPG. So in the questions they are asking about the HOPG, which means the highly oriented pyrolytic graphite. If its Mohs spread angle is less than 1%. So Mohs spread angle is what? So here you can see this is A is the Mohs spread angle. That means the spread of polycrystalline graphite tiles should be so flat that two adjacent tiles never have a misalignment which is less than the 1 degree. So this HOPG highly oriented pyrolytic graphite is a polycrystal similar to mica, and it can be also exfoliated to produce the single graphite layers. Single graphite layers, which means what? The graphene is having a single layer, which that's why it has some very good electrical and the other properties such as mechanical and thermally property. Now, the application of HOPG is what? Crystal optics, X-ray diagnostic tools and spectrometers, ion beam detectors as electrode and the conductive supports, test samples for various instruments, other methods, graphite precipitation from carbides, metal silicon. So here the question is asking about the HOPG is different from pyrographite because of what? Pyrographite, here I showed you, and this is your HOPG. Okay, so the answer is it has a highly aligned crystals. Okay, which I have explained here, because HOPG is polycrystal similar to mica, and also it is a highly aligned oriented pyrolytic graphite if Mohs is less than 1%, less than 1%, and so that's why it is highly aligned crystal. Now the second question is uh, change in the enthalpy of formation of a hydrocarbon gas from negative to positive at a certain temperature indicates that it becomes more stable compared to other hydrocarbons. It cannot be used as a precursor for graphite. It is thermodynamically favorable to obtain it during pyrolysis of a polymer. It is thermodynamically favorable for it to dissociate. What could be the right answer? Any guesses, or can you give me, if you have watched the lecture, that what could be the right answer for this question? Yes, so I hope that you got the answer for this. So let's discuss again. So this slide I think I have taken. So in the pyrolysis, so what is pyrolysis first of all? So it's an thermochemical decomposition of a solid, liquid, or gas phase hydrocarbon in the absence of oxygen. So the solid state pyrolysis is thermosetting resins, petroleum cokes. We do the solid state pyrolysis of these products, and the liquid phase pyrolysis is petroleum pitches and some polymers. For that we do the liquid phase pyrolysis. Now the gas phase pyrolysis is hydrocarbons such as methane, acetylene, chemical vapor depositions that we do, and all forms of pyrolysis are used for carbon manufacturing, various graphitizing, non-graphitizing carbons, as well as crystalline graphite. So the question is that what happens during the pyrolysis? So the hydrocarbons are broken into smaller molecules. Non-carbon atoms are released after cleaving from parent atoms. Some cyclic carbon structures are formed. Combinations of 1 and 3 is also possible. So the formation and the dissociation of compounds depend on their enthalpy of formation. Change in enthalpy for getting 1 mole compound from its element is nothing but known as enthalpy of formation. To form or to change in enthalpy for getting or to form 1 mole compound from its element, and stability at a temperature. So we require a negative enthalpy value for compound formation. We need positive enthalpy for the compound dissociation. So when we talk about the formation, the enthalpy should be negative, but when we talk about the decomposition, then the enthalpy would be positive. So for example, formation of methane in a polymer pyrolysis will occur if methane is very stable at a given temperature. On the other hand, the pyrolysis of methane itself will take place if it is not stable at a given temperature. So this is the slide about the, but in the question there are some enthalpy of formula hydrocarbon has a negative to positive at certain temperature indicates what? So it's saying the negative to positive. So definitely indicates that it is thermodynamically favorable for it dissociates. Okay, because in the positive enthalpy, the compound needs to decompose. So the favorable for the dissociate when it's from the negative to positive. I hope it is clear. If any doubt, then you can ask me that. Is there any doubt in the enthalpy of formation? This question can be asked in your assignments and in exam. Yeah, so the next question is the Keys graphite is formed when? So it is asking about that about the regarding the temperature and pressure. So the first is like a temperature or pressure is below the liquidus line on the phase diagram. Temperature or pressure is above the liquidus line on the phase diagram. Temperature or pressure is below the solidus line on the phase diagram. Temperature or pressure is above the solidus line on the phase diagram. So if you know the phase diagram for this graphite, then probably you might answer that where it forms. So can anybody guess or give their answer that what could be the answer for this question? Yeah, so let's discuss about where it actually forms. So in this slide, you can see about the Kish graphite. So the Kish graphite usually precipitates during the steel manufacturing on the melted iron surface along with the other residues. So it is basically refined using sieving, flotation, milling, magnetic separation. So many methods are there, so by which you can refine it. and up to 99% purity and scale large flakes can be achieved in this. So yeah, you can achieve a very high purity graphite. It grows as dendrites which form plates, actually may span up to several centimeters, and the thickness could be around 0.01 to zero point 0.1 mm. And fast cooled uh, 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 Kish graphite has thinner plate. But actually, the thing is, the longer dendrites and the slow cooled has thicker plates and the less spread. Now, the exist in the form of a small platelets, and that are powder or directly used in various kinds of application. So the mechanism of formation of this graphite is that when carbon iron alloy melt is cooled below the liquidus temperature, the important part is below the liquidus temperature, carbon precipitates as a graphite. So now this is atomic deposition of carbon. So if the deposition is layer by layer, under sudden changes in temperature, graphite is formed. The growth mechanism involves nucleation growth and spread of the crystal in rapid manner. Now, this pitch graphite is usually used indirectly or after pulverization in batteries and related other applications. And this is also similar to the natural flake graphite, but actually, the industrially the term kg is more common. So now the liquidus line is what in the equilibrium phase diagram is the line. So it is the line between liquid and the liquid and liquid solid phase. So this is the liquidus line. So I hope this is clear that where it forms uh, below or above the liquidus temperature. Now you can give me the answer for this question. It's very simple now. So, so as you can see, the answer is the temperature or pressure is below the liquid dust line on the phase diagram where your pitch graphite will form. So the below the liquid dust diagram is the answer A. So now the next question is, if a polymer features a high carbon content, it will always yield graphite, always yield glass-like carbon, yield either a graphitizing or non-graphitizing carbon, never yield non-graphitizing carbon. So can you now give the answer, or you can also type in the comment box. You can guess or you can give if you have watched the lectures. So this question is asking about if a polymer features high carbon content, it will always yield graphite, yield glass-like carbon, or yield either graphitizing or non-graphitizing carbon, or never yield non-graphitizing carbon. So any guesses what it could be? Or if not, then probably you can see this slide and now you can answer. Can you just read the slides for the answers? And then probably you might know the answer. Then I'll discuss that how it could be, what it features actually. So now here you can see the classification of the polymer derived carbon. So there's a polymer. When you do the carrying, then you will get the activated carbon and the low purity gas. And by coking, you will get a pyrolytic graphite, coke, and the glass-like carbon. So this pyrolytic graphite and coke is your graphitizing. You will get from the graphitizing, but the glass-like carbon, activated carbon, and the low purity charges from non-graphitizing. This pyrolytic graphite is also the highly oriented HOPG, as we have discussed, highly oriented pyrolytic graphite, and HC means hydrocarbon pyrolysis. So here in the image, you can see the glass-like carbon, how it looks actually, and the activated carbon. So it has various applications because of its exotic properties. So usually the non-graphitizing carbons are those which cannot be converted into graphite even heated up to 3000 degrees centigrade. They have complex structures formed by the curved carbon hydrocarbon sheets during pyrolysis itself. Such structures have curls, folds, and spherical units which cannot open and become graphene seeds. Now, the graphites, glass-like activated carbons are non-graphitizing carbon, but with very different properties actually. So, so that's why the polymer features a high carbon content. So it's either yield the graphitizing or the non-graphitizing carbon. Here you can see the polymer. It's asking about the high carbon content polymer features. So it could be graphitizing or the non-graphitizing both. Yeah, right. So your answer will be the either, yeah, graphitizing or non-graphitizing carbon. Now, again, the same question. I hope this would be very simple to answer. A graphitizing carbon is a type of synthetic graphite, a carbon that can be converted into graphite, highly graphitic carbon, a polymer that can be converted into carbon. Can you guess now? Just now we have discussed it that what could be the appropriate answer for this question. Yes. So the graphitizing and the non-graphitizing carbon, if you will see here, you can see in the image that how the graphitizing carbon looks and how the non-graphitizing carbon looks. And the first image is corresponding to the graphite. So if a carbon material does not obtain a 3D crystal structure even at 3000 degrees centigrade, it is called non-graphitizing. Okay. These materials do have a short range order, and but in addition to flat graphene sheets, they also contain curved carbons, as you can see in the image below. But main crystallinity measurement techniques for graphitic carbon are X-ray diffraction, transmission electron microscope, and Raman spectroscopy are the majorly techniques for measuring. In X-ray diffraction, crystallinity is determined by measuring the diffraction angle of X-ray, which indicates bond length. Sharp peaks implies most bonds are of same length. So here the non-graphitizing carbons features a range of bond lengths, hence a hump. You will get a broad peak in the non-graphitizing carbon. But in case of graphitizing carbon, you will get a sharp peak. As you can see, it is highly ordered, but it is randomly oriented and like a curved, not any having a sharp feature. So I hope, do you have any doubts? If you have, then you can probably ask me any question if you will have. Or you can also type in a comment box. Hello. Yes, hello.
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 Yeah.
Good. Yeah.
Hello. Hello.
Hello.
Am I audible?
Uh, mm,
Hello.
Hello. Is the class of carbon manufacturing novel here?
Yes, this is the class. So you joined. Are you student?
Yes.
Okay, but you joined very late.
Yeah. So is it over?
No, no, it's running actually. Hello.
Hello. Okay.
Yeah. So it's running actually. So I'm conducting a class. So do you have any doubt?
Currently, no. I'm just hearing the questions and answers.
Okay.
Hello.
Okay. So do you know? Okay. So I'm discussing some of the question and I'm discussing with the students and also I'm asking the question. Okay.
Okay.
Yeah. So have you watched the lectures? All the lectures?
Yeah.
Okay. So do you have any doubt?
Actually, I'm no, no. I'm just starting the fourth week lecture. So
You have not completed?
completed. I'm continuing. I'm not over it.
Okay.
Thing.
So okay then. Okay, then let's discuss this question. A difference between coking and carrying is that coking is a property of natural polymers while carrying happens in synthetic polymers. Coking yields graphitizing carbon while carrying yields non-graphitizing carbons. Coking yields black carbon while carrying yields brown carbon. Coking yields carbon with flat surface while carrying yields porous carbon. So do you know that what is coking and carrying and what it actually yields? So now the polymer derived carbon. So here the pyrolysis of polymer does not always yield graphite. So there are two primary mechanism of carbonization of polymer. So it's coking and carrying. So coking is if during its carbonization the polymer passes through a liquid or semi-solid state at least once. And carrying, if during carbonization the polymer structures remains rigid and does not pass through any liquid state. So the combination of both mechanism is also possible. In both cases, there is a net mass loss from the material which leads to shrinkage or porosity. So coke carbons are dense and jars are porous. So here you can see the coking and in carrying you will get a porous kind of a structure. So these are so here they're asking a difference between coking and carrying is that. So here a coking yields carbon with flat surface while carrying yields with porous carbon. Here you can see it is highly porous and it is like a solid and a flat surface. So I hope it is clear. So the which of the following carbons is obtained when a polymer undergoes carrying during heat treatment? HOPG, glass-like carbon, porous carbon, or the pyrographite? So I think this you can probably answer from here. So polymer undergoes carrying treatment. So porous. So in carrying, you can easily see the porous carbon we can obtain as we have already discussed. So the answer is porous carbon. Now the thermal cracking of gaseous hydrocarbons followed by pyrolytic graphite. Graphite deposition is also known as calcination, combustion, chemical vapor deposition, or carbonization. It is easy one we have discussed earlier. So now you can quickly answer this question. So yeah, in the pyrolysis is the thermochemical decomposition of organic materials in the absence of oxygen. The decomposition of the hydrocarbon must be mainly thermal, and that is the other chemical reactions such as oxidation should not be included. Pyrolysis is not just limited to polymers. Any organic materials can be pyrolyzed. Pyrolysis always yields some solid carbon, but depending upon the pyrolysis condition and precursor, the fraction and the purity of pyrolytic carbon may vary. Gaseous hydrocarbons can also be pyrolyzed. In this case, the process is also called cracking. Gases requires relatively higher temperature and a catalytic support where carbon can be deposited. A refined version of this process is also known as CVD, chemical vapor deposition, which is used for making carbon nanomaterials such as graphene and carbon nanotube. So this is the CVD. So the answer is your chemical vapor deposition through which we can uh, deposit this pyrolytic graphite. Now, um, so which of the following takes place during the pyrolysis of the polymer? Polymers chains align to form graphite crystallites, and the d-spacing between carbon sheets is reduced. Various hydrocarbons radicals are generated. Polymers molecules break into volatile and non-volatile hydrocarbon. So here when you will see the pyrolysis. So inert heat treatment of polymers consists of the following steps. So first one, as you can see, the removal of water, solvent, volatile impurities up to 200 to 250 degree, then cleavage of C double bond O and cleavage of C triple bond nitrogen, cleavage of CH bond and formation of CC bonds, and increase in La and Lc. So this is your 1 to 4 is pyrolysis, and the 1 to 6 is heat treatment. Since the first step of the process is pyrolysis, often entire heat treatment is called the pyrolysis. The exact temperature values for the different segments can vary depending upon the precursor to precursor, and also the heating rate and environment also influences the pyrolysis chemistry. During pyrolysis of the polymers, multiple reactions take place usually, and the several radicals form, dissociate and reform new hydrocarbons, and the new fragment are generated. So micro and nanoscale structure may graphitize at temperature as low as 900 degrees centigrade. So here the usually so that's why the various hydrocarbons radicals are generated as well as the polymer molecule break into the volatile and the non-volatile hydrocarbons. So here the all polymers undergoes the pyrolysis between 600 300 to 600. So yes, here you can see the, so that's why it is called the pyrolysis is from 200 to the 700. So all hydrocarbons yield some fraction of carbon on heat treatment. So when you will see, I have already discussed, so that's why it's always true, the hydrocarbon we will find some fraction of the carbon. Carrying polymer doesn't pass through a semi-solid phase during its carbonization. So actually here you will get a porous structure. So that's why it is true. So in X-ray diffractogram of a non-graphitizing carbon, all peaks are sharp. So actually it is far, because in non-graphitizing you will get a amorphous kind of a structure. So that's why you will get a hum kind of a structure. Non-graphitizing carbons exhibit a short range order, hence they can be converted into graphite at heat treatment greater than 3000 degrees centigrade. So actually this is false. When you will see, this is a graphitizing of the coke and also the pyrolysis mechanism. So yeah, so these are the some slides. There you can also get some concepts. So I hope if you will have any doubts, so I have tried to cover the most of the questions that could be related to your assignments in the week 4. And if you will have any kind of a doubt regarding your assignments question, then let me know. We can further discuss these questions in our next class. So yeah, thank you. Goodbye.